Good morning. Let's start our today's lecture. And the title of this lecture is Quadratic Surfaces Ending and Gaussian elimination method. The second part is a new theme, and this theme will be devoted to the consideration of the classical elimination method of solution of linear system. And in a previous term we consider this method, but now we are going to study more deeply this method, and we will apply this method to consideration of various problems of linear algebra. And first we are going to finish the study of quadratic surfaces. On the previous lecture we consider the main examples of quadratic surfaces, and I recall that we have the following examples of quadratic surfaces, and more precisely we have a full list of such surfaces. More exactly, a full list in general position. We have also some examples of so-called degenerate cases, but in the general position we have the following examples of the quadratic surfaces. First of all, sphere, cylinder, cone, ellipsoid, simple hyperboloid, double hyperboloid, elliptic paraboloid, and hyperbolic paraboloid. And we have the following equation which define these surfaces. And I write now the equation of double hyperboloid. Elliptic paraboloid, and hyperbolic paraboloid. The main theorem asserts that arbitrary surfaces of the second order can be reduced to the one of these cases. I recall that arbitrary surfaces of the second order can be defined by the following polynomial of the second order, namely a11 x square plus a22 y square plus a33 z square plus 212 xy plus 213 xz plus 223 yz plus a1x plus a2y plus a3z plus A0 is equal 0. And quadratic surfaces can be defined as a set of the points in the space which have the following coordinates x, y, z, which define the equation f x, y, z is equal 0. Any surfaces. And the main idea of the proving of this theorem is the same as the case of the quadratic curve. We can grouperize the term which contains unknown variables x, y, and the main idea of proving. We can rewrite the polynomial f in the following way. I can consider the term which contains variables x and y, the quadratic term which contain x and y, and after them we can consider the term which contains the quadratic term which contains variables x and z, and after them the terms which contains y and z. Z square, and after them we write the linear term. And we have three groups of the term. First of this group of the groups contains quadratic terms which variables x and y, and we have the same case as the case of the curve of the second order, and we can apply rotation method, and we rotate the coordinate system x and y, and after them we rotate this variable, and any rotation can be decomposed in the series of such rotation, and we can get the final rotation which reduce this equation to the canonical form. But later we can consider some general method reducing such expression to the canonical form. We have so-called example of so-called quadratic form, and this quadratic form has the following matrix. The symmetric matrix. And later we consider the general method of diagonalization of this matrix, which reduces matrix to the diagonal form. And this theorem is a consequence of this general method of diagonalization of the quadratic form. But now we restrict themselves to the consideration of these concrete examples of diagonal form of general equation, general quadratic form, general quadratic surfaces, general quadratic surface. And I recall that in the previous lecture we consider the first four examples of this form. The sphere. The sphere is defined as a quadratic surface, which defined the following condition: any point of this quadratic surface is defined by the following condition: the distance between this arbitrary point M, its coordinates x, y, z, and some fixed point M0 is coordinates x, 0, y, 0, z, 0 is constant and equal r. And this condition can be rewrite in the following form: the length of the vector m0 m is equal r, is equal r, and is equivalent condition the square of length of this vector is equal r square. The square of distance is equal scalar or dot square, and this condition can be rewritten in the coordinate form as we have the coordinate of the vector m0 m is x minus x0, y minus y0, z minus z0, and we obtain the following equation of the sphere: x minus x0 square plus y minus y0 square plus z minus 0 square is equal r square. We obtain the general equation of the sphere in the space. If we choose the origin of the coordinate system which coincides with point M0, we obtain the canonical equation of the sphere x square plus y square plus z square is equal r square. This general method, which is the same as the method of obtaining of the equation of the second order curve. In the case of quadratic surface, we have the same method to obtain the equation of the surface. In the case of cylinder, we have the same equation as in the case of the curve. For example, we have equation in the form x, for example, x square plus y square is equal 0. In the plane, this equation defines the curve in the plane in the coordinate plane x or y, and in this case we have the circle. But in the space we have third coordinate z, and if a point M0 with coordinate x, y0 lies on our circle, the arbitrary point with the coordinate x0, y0, 0, let's denote this coordinates by these letters, and let's consider the point with coordinate x0, y0, which coincides with coordinate of the point M0, and this arbitrary coordinate z. This point, this coordinate also satisfy this equation, and we have straight line which parallel to the coordinate axis, coordinate x or z, and this straight line belongs to our quadratic surface. And in this case, we obtain so-called cylinder. But we have the same reasons when we consider the arbitrary equation of the second order curve. And in this case, we obtain other examples of the cylinders. For example, we have equation y is equal to y square is equal to px, the equation of parabola, and in this case we obtain the cylinder, parabolic cylinder, and the same way we can obtain the elliptic cylinder, hyperbolic cylinder, and also we can consider change coordinate x, y on the coordinate x, z or y, z, and we obtain the cylinder which contains the straight line which parallel to other coordinate axis. And the canonical equation of the cylinder has the following equation: f x y is equal 0, and f be the canonical equation of the second order curve canonical equation. In this case, we have in general position 3 examples of the cylinder: elliptic, parabolic, and hyperbolic cylinders. And let's mark this cylinder: elliptic, hyperbolic, parabolic. And third example, cone. I recall what does mean cone. The second equation if we fixed the variable z is some constant, it means that we consider the section of our curve by the plane which parallel to the coordinate plane x or y. C. And in this, for example, let z is equal exactly c, which the fixed constant in the definition of equation of the cone. In this case, we obtain the equation of the ellipse is with defining constant a and b, and in this case we obtain cone. If we will change this plane and we move this plane parallel to the coordinate axis, and let we consider C1 which less than C. In this case, we obtain the equation is equal C1 square divided C square, which is some constant which less than C. And in this case we can divide this left and right side on this constant, and we obtain the ellipse which less than this one. And in the case when this constant is equal 0, we obtain the point. If we put the value of y is equal 0, we put x is equal 0, and we obtain the section of the coordinate plane x is equal 0. In this case, we obtain the equation y squared divided b squared minus z squared divided c squared is equal 0. This equation can be rewritten in the following form: zb minus y divided b minus z divided c times y divided b plus z divided c is equal 0, and we obtain two straight lines which lies in the coordinate plane YOZ. The same way we obtain the section by the other coordinate plane XOZ, and we can imagine the form of this cone, in the section of the coordinate plane which parallel coordinate plane X or Y. We obtain the ellipses, and we obtain the following contours, and the traces of these surfaces which can be obtained at the section by the other coordinate plane XOZ and YOZ. In this case, we obtain the pair of the straight lines. And we obtain such example of the surface of the second order cone. Easy to see if we consider the section of other plane. In this section, we obtain other curve of the second order. For example, if we consider the plane, the arbitrary plane which parallel coordinate plane, for example, YOZ. In this case, if you put z, if you put, for example, x is equal some constant. For example, x is equal a. In this case, we obtain the equation of the hyperbola. If you substitute these values in the equation of the cone, we obtain the following equation: 1 plus y squared divided b squared minus z squared divided c squared is equal 0. And this equation is the exact equation of the hyperbola: z squared divided c squared minus y squared divided b squared is equal 0. And I obtain the section hyperbola. And we can change, and in this case, some constant. And for various values of this constant, we will obtain the various type of hyperbolas. If you move this section, we obtain as a hyperbola, but these hyperbolas are the same. These hyperbolas have the same form, but values of the parameters b and c. And when c is equal 0, we obtain the pair of the intersected straight lines. The following example, ellipsoid. And we also consider the section of these surfaces by the straight line. We consider traces and contours in the case of ellipsoid. So we have the following defining equation: x squared divided a squared plus y squared divided b squared plus z squared divided c squared is equal 0. And as in the previous case, we consider the various traces of these surfaces. Namely, we can consider the intersection of the section by the coordinate plane. For example, I can consider coordinate plane z is equal 0, and in this case, in this plane, we obtain the equation of ellipse with parameter a and b. X, y, z, a minus a, b minus b. We obtain the ellipse. The same way, if we consider x or y, if we consider the trace by the other coordinate plane x o z, for example, in this case we obtain this section z is equal 0, y is equal 0. In this case, we obtain the equation x squared divided a squared plus z squared divided c squared is equal 0. And in this case, we also obtain ellipse. And in the section of the x is equal 0, the section by the coordinate plane y o z. In this case, we obtain the equation x squared divided, y squared divided b squared plus z squared divided c squared is equal 1. And and we obtain also the ellipse, and we obtain the surface of the following form. We obtain the following, the surface of the following form. We obtain the section of the surface by the all coordinate plane are ellipses. And the question, yes.
Why did you put x and y and z equal 0?
Okay. If we put one of the coordinate z is equal 0, we obtain the coordinate plane. For example, we have point with coordinate x, y 0. Easy to see that we obtain the point which lies on this coordinate plane, x, o, y.
And it's the
yeah,
ellipse, right?
Yeah, we obtain the ellipse. In this equation, we put this coordinate is equal 0. And in geometrical sense of this algebraic operation is the intersection these surfaces which define by this equation and the plane which defines this equation. We have the system of two equations. By algebraic way, we have the system of two equations. But geometrical sense of this system of the equation is intersection of this geometrical methods and this. The intersection of the surface and this plane. And if we substitute z is equal 0 in this equation, we obtain the equation x squared divided a squared plus y squared divided b squared is equal 0. And we obtain the equation of ellipse. And we obtain that the section of our quadratic surface by this coordinate plane x, o, y is the ellipse. And we draw the ellipse in the coordinate plane. Okay? The same way, we also can consider the sections of the other coordinate plane. For example, x is equal 0. And we substitute x is equal 0 in the equation of the surface. And we obtain also the equation of the ellipse in the plane y 0, z. And in this case, we also obtain the ellipse. And okay. The other way is the following. We have the equation ellipse And this ellipse we can rotate in the we can rotate so that the OX is the line of symmetry of this rotation, and Y, if we have some point with coordinate, we have coordinate x, y, x 0, y, and if we rotated the point with coordinate y, we can change this coordinate by y square. We can change on the coordinate y square plus z square. If this coordinate, if this coordinate is, for example, is equal b, if we rotate this point, we obtain the point with coordinate y square plus z square, which equal y square. And we substitute this expression to this, and we obtain so-called rotation surface. Y square plus z square divided b square is equal 0. In this case, both parameters b and c are equal, and we obtain the rotation surface. But this rotation surface we can shift it one on the, for example, in the direction of coordinate axis OZ, and we obtain the arbitrary ellipsoid. And other way to obtain the equation of arbitrary ellipsoid. This way, first step, we consider the rotation surface, we consider ellipse, rotate this ellipse relatively one of the coordinate axis, for example, relatively coordinate axis OX. After then we obtain rotation surface, and third step, we shift this ellipse and obtain the arbitrary ellipsoid. And in the reverse way, we consider the equation and consider the some section of this surface by the coordinate plane or the plane which parallel to the coordinate plane. And in this case, we obtain in the section the ellipses. And ellipsoid reflects this fact that this figure has a form such that any section of these figures of these surfaces by the plane which parallel coordinate plane. All these sections are ellipses. And second example, simple hyperboloid. What does mean simple hyperboloid? Simple hyperboloid. simple hyperboloid has the following defining equation: x square divided a square plus y square divided b square minus z square divided c square is equal 0. Let's consider the various sections of this surface. First of all, consider the section of the surface by the coordinate plane z is equal 0. Z is equal 0. Easy to see that in this case we obtain the equation of the ellipse. And we obtain the ellipse with parameters a and b. If we shift the plane and consider the other coordinate plane, the other plane which parallel to this coordinate plane z is equal 0. For example, z is equal some constant. For example, c. And in this case, we obtain also equation of the ellipse, but with other parameter 2. And we can divide it, this parameter. And easy to see, we obtain also ellipse, but the parameters root square 2a root square times b, more larger ellipse. And if this constant increase, the sizes of the ellipse, which we obtain as a section of this plane, became larger and larger. But the form of this ellipse is the same form. Yeah.
This formula is for ellipse or for hyperbola?
Yeah. We can better to understand the form of our surface if we consider the other section by the other coordinate plane. For example, let's put y is equal 0. And in this case, the intersection of this coordinate plane and our surface is a hyperbola. In this case, we put y is equal 0, and we obtain the equation x squared divided a squared minus y squared divided b squared is equal 1. And in this plane, we obtain hyperbola. In this case, we obtain also hyperbola. And other section, if we put x is equal 0, and in this case, we also obtain the hyperbola. So we obtain the following surface which has the following form. If we consider the section by the plane which parallel the first coordinate plane XO0, we obtain in this case the ellipse, and if we consider the section by the other coordinate plane which parallel by other coordinate plane y or z and x or z, we obtain the hyperbolas. We obtain the hyperbolas. And if you put this coordinate is equal 0, we obtain the equation of hyperbola. This also hyperbola, and this we obtain the ellipse. Easy to see. All these cases. This one is absent, hyperbola. This one is absent, hyperbola. This one is absent, we obtain ellipse. Do you understand it?
Yes. Question.
Yeah.
If, for example, A, B, and C are arbitrarily small, X, Y, and Z are arbitrarily small, then our hyperbola will be a very small line, right?
If X and Y cannot be enough small, let's put X equals 0, Y is equal 0. This okay. If this one is equal 0, this one is equal 0, this one is negative, non-positive. This one is non-positive, negative or 0. But this one is positive. And this point, when both x and y is equal 0, is not belong to our surfaces. And easy to see this case. If two coordinates is enough small, this point lies in the interior of the domain of the surface, which interior of our simple hyperboloid, but not on the surfaces. Okay, do you understand?
Thank you.
Yes. Okay. The interior of this ellipse, if we consider the cylinder, which the cylinder lies in the interior of our surface, strictly in the interior, in the intersection of this ellipse of our hyperboloid and this cylinder. And if you put, we also can consider the cone x squared divided I squared plus y squared divided b squared minus z squared divided c square is equal 0. This cone line lies strictly. Okay. We have our hyperboloid. We have the equation of hyperboloid and equation of cone. This cone lies in the interior of the hyperboloid, and if you can consider section by the plane, by the coordinate plane y or z and x or z, in this section we obtain hyperbola and a pair of intersected straight line. And this intersected straight line are the asymptotes to this hyperbola. And in the case of the surfaces, we obtain the asymptotic, this conus is asymptotic surfaces to this simple hyperboloid. The distance between a point of the cone and the point of simple hyperboloid, when the point goes to the infinity, when the all coordinates goes to infinity, the distance goes to the 0. If you consider 2 points, one of this point lies on the cone, and consider the distance between this point and hyperboloid, infimum distances between this point and all points of the hyperboloid. This distance, this minimum of the distance goes to the 0, And in this case, we will say that the cone is an asymptotic surface. Okay, and other example, double hyperboloid. We change sign in the right side. In this case, we have sign plus. In this case, sign minus. The left side of both this equation is the same. We have the same side. If we change the sign, what we obtain if we put first coordinate is equal to 0 and the second coordinate is 0, we obtain the hyperbolas. But if we put the third coordinate, we obtain the imagined ellipse or empty set. And what does mean? How to change the form of this surface. let's z is equal 0. In this case, we obtain x square divided a square plus y square divided b square is equal -1. And we obtain empty set. If z is equal c. Easy to see if the constant, let's put z is equal some constant. And if this constant less or equal c, we obtain in this case empty set, because this term less than unit. And if we transfer in the right side, we will be obtain the numbers which less than 0, negative numbers. But in the case when z is equal c, we obtain that this term is equal -1, and after transferring in the right side, we obtain that the sum of this term and this is equal 0, exactly is equal 0. And in this case, we obtain the equation x square divided a square by y square divided b square is equal 0, and we obtain the point. If z is c, we obtain point. And by symmetrical way, if z is equal minus c, we also obtain the same equation. This equation is defined. This equation defines exactly one point set. If z will be greater than c1 greater than c. In this case, we obtain c1 square divided c square minus 1, and this quantum greater than 0, and we obtain ellipse. And easy to see, we will obtain the ellipse. In this case, also ellipse. But if we consider a section by the other coordinate plane, if we put y, for example, x is equal 0. X is equal 0. In this case, we obtain in this plane we obtain the hyperbola. X is equal 0, we obtain a square divided b square minus z square divided c square is equal -1, or z square divided c square minus y square divided b square is equal 1. And we obtain the equation of the hyperbola in this section. And in this case, we obtain two parts of this surface. And double hyperboloid, the name double hyperboloid reflects this fact. This surface has two parts. Excuse me, I want to return to the double hyperboloid. In this case, easy to see that we have in the case of the simple hyperboloid, we have the following interesting fact. We have infinitely many straight line which lies in this surface. And this simple hyperboloid contains two pencils of lines. We have such families of the straight line which contains in the hyperboloid, and any point of hyperboloid belongs one of these lines. And we have the other family of such lines, and we can obtain exact equation for this family, namely let p plus minus the one of this straight line, and this straight line has the following parametric equation: a cosine alpha, b sine alpha 0 plus t minus a sine alpha b cosine alpha plus minus c. Namely, we obtain the following parametric equation for this straight line: x, y, z is equal a cosine alpha minus t a sine alpha b sine alpha b sine alpha minus plus first minus plus t cosine alpha, maybe, and plus minus c. This parameter is defined the direction of this straight line. Easy to see if you substitute this expression to the equation of the simple hyperboloid: x squared divided a squared plus y squared divided b squared plus z squared divided c squared is equal to 0. We can substitute this equation in this, and we obtain a squared divided a squared cosine alpha minus t sine alpha square plus b squared divided b squared sine alpha plus t cosine alpha square plus c squared divided c square. and easy to see a square is killed, another is b square divided b square is equal 1, and we obtain the following expression: cosine square alpha minus 2 cosine alpha sine alpha plus I'm sorry. Sine square alpha okay, that's all right, plus sine square alpha plus 2 sine alpha cosine alpha plus cosine square alpha minus, I'm sorry, minus 1 is equal cosine square plus sine square 1, sine square plus cosine square 1, and plus 1 minus 1 is equal 1. And we obtain that this straight line belongs to our surface. Okay.
Could you please explain what is p plus minus t?
We have two families. This equation of the equation of the straight line in the space. I rewrite this equation. P plus minus is a coordinate, the coordinate vectors. P plus minus t is some vectors x, t, y, t, z, t. And left side the sum, the equation of the line in the space. The coordinate of the line in the space. We have one parameter, and three coordinates depend on this parameter, and we obtain some line in the space. Easy to see that this line for fixed alpha is the straight line. If we fixed alpha some parameter, and we obtain the straight line which pass through the point with coordinate a cosine alpha, b sine alpha, c plus minus c, the initial point of the straight line. And we have the parameter t. If we put t is equal to 0, we obtain some initial point. And we have a directed vector. This vector has this coordinate a sine alpha, b sine minus, b cosine alpha, c. It has the coordinates of this vector. This vector rotates in the space, and rotation, the angle of rotation, alpha. The angle of rotation. The second coordinate is fixed. And we obtain the sum family of straight line, which rotated and moved in the space. And rotate and moved in the space. And this rotation give the surface of simple hyperboloid. A simple hyperboloid. this straight line, rotate and moved in the space. And this rotation moving gives us this simple hyperboloid. This such interesting fact. Okay, yes. Any questions?
This straight line gives us, when it rotates, gives us two simple hyperbola, right?
Simple hyperboloid, yes. Exactly. We have two families. One family moved in, and in any point, through any point, for any point, we have two straight lines which pass through this point, through straight line which intersect in this point. And one straight line moves by this way and rotate and moves, and other straight line moves and rotate. We have two families. Two family of straight line, or two straight line which moves, and two straight lines from various families intersect in any point. But in the various point, we have various intersected straight lines from these two families. But for any point, we have two straight lines from these families which intersect in this point.
So our hyperbola is somehow tangent to our lines, and sometimes intersects, right?
Yeah. Yeah, we have two families, but the equation of this family the same. The difference between this equation only in the third term. In this case, we change sign. We change sign of this vector, and in this place, and also change this. This direction such, this direction such, and an opposite direction in the third coordinate. Okay, yes. Have any time? Haven't? Уже время закончилось? Excuse me. This. I have any time, and I cannot consider the second two example, elliptic paraboloid and hyperbolic paraboloid. In the case of hyperbolic paraboloid, we also have the same family of straight line which have the same property from the any point of hyperbolic paraboloid for the any point of hyperbolic paraboloid. We have also two intersected straight line which contained in this hyperbolic paraboloid, and I try the equation, but maybe in the following lecture. I'm sorry, I'm going to consider second part, Gaussian elimination, but next lecture we are going to consider. Thank you for your attention. Thank you.